Hello everybody, this is Nicholas Zabaras. This is Statistical Computing and Machine Learning. So today will be our first lecture on linear regression models. So we will try to start doing some machine learning applications, and in particular, we'll discuss about supervised learning type of problems. So today there will be nothing literally probabilistic or Bayesian in our setting. So we will talk mainly about polynomial regression models, in particularly because I'm interested to bring up the ideas of overfitting, the effect of the data size, and also to introduce things such as the training and the test data sets, the concept of generalization, and also for us to see that the well-known least squares type of estimates for these regression problems, they are actually identical to maximum likelihood estimation. So today also I will discuss briefly the idea of regularization, but we will see most of the details of regularization in the follow-up lecture on regression models. So I will only make a remote link with probabilistic models to give you sort of a high-level presentation of the frequentist approach to regression models versus the Bayesian approach. But again, all the details of the Bayesian setting will be on follow-up lectures. So today we will talk about basis functions models. We will discuss MLE and Least Squares. I will also give you some algorithms for sequential maximum likelihood estimation of the regression coefficients, and we will see back in use the Robbins-Monroe algorithm that we discussed in an earlier lecture. And then we will finish today with a brief discussion of robustness and how we can modify these least squares estimates or these Gaussian likelihood models so that somehow they can give us more robust performance than a Gaussian model can. So the goals for the lecture today will be to discuss what is a regression problem, to learn about these issues of overfitting, the effects of the data size, and also introduce many related concepts: training data set, test data set, overfitting, generalization, and the like. We will focus primarily in least squares type of problems, and we will see again that MLE estimates are identical under Gaussian likelihood to this, to the least square solutions. We will learn about the design metrics. So that's the metrics that we organize our training data set. We will learn about basis functions and future space. This will be useful pre-processing steps for regression models. All right, so let me remind you of a supervised learning problem that we have seen many times in the course in earlier lectures. So what you see on the bottom is these digits from 0 to 9. They are handwritten digits. And the classification problem basically will be to train an algorithm that somehow from some training data like the ones that you see in these pictures with the affiliated labels. So for example, I am going to give you this image, and at the same time I'm going to tell you that it's digit 3. I'm going to give you this image and I'm going to tell you that it's digit 2. So what your objective will be to produce a function that somehow is capable to tell me for a new test data point x what digit that point represents. Okay, so what we discuss is basically the training data set that involves both this x label, these x images, right? These images are vectors that I call them x, but also I give you the labels t for each image. I tell you what digit it represents, and your objective is to build this function y of x that somehow for any x you can tell me what digit that x is affiliated with. So we define the training data set, and the training data set involves x1 to xn. So these are my images, but also the corresponding target vectors. And then we discuss about the test data. These are points that we have not used at training. And the idea here is we try to generalize, we try to produce a function that will tell us what digit x belongs. Now, I call these vectors, even though they were images, but you can think if you take these images and you put them in a vectorized, pixelized form, you will get a very long vector, and that's what I refer with as x1, x2 to xn, and also x on this slide. So this is a supervised learning problem because I give you both the x's and the targets, okay? And so we have seen the training, we have discussed about the test and generalization. Let me say something about future extraction as a pre-processing step. The idea here is sometimes it's more convenient to work in some other space rather than the space of x. So if x, let's say, is a vector in Rn, maybe we need to map this to another space. Why? Maybe in the other space classification, for example, will be easier to perform. So the idea here is to come up with some mapping, if you like, from the original x space to this new future space, or equivalently to extract futures out of the original x's. So this engineering of futures has been a key area of research in machine learning in the 70s and the 80s. And we will discuss it in the lectures today, at least so we can have a concrete view as to what this implies for regression models. Okay, so that's the supervised learning problems in the context of classification. The same thing we will see today in the context of regression. The only difference in the context of regression is that the labels, they are not discrete class labels, but they are real numbers, all right? So that's the only difference. So our labels will be real numbers, or they can actually be vectors of real numbers. Now, there is a whole other subject area of machine learning that goes with the name unsupervised learning. So here I give you the training vectors x1 to xn, and I ask you to sort of cluster them, figure out, from what classes maybe this data came. Maybe you have to do what's called a density estimation. Maybe you have to find some reduced representation of this data because maybe these vectors, they live in a lower dimensional subspace of their original space. So these problems are unsupervised, and we call them unsupervised because we only give you the x's, we don't give you the targets t the way we had for regression and classification problems. And then you have the third category that I give you literally very little, and that's the whole area that's called reinforcement learning. Reinforcement learning is a little bit closer related to the ideas from robust control theory. But, if you can think somehow the problem of trying to move from A to B, and you move in steps, and in every step you move, you receive some signal or some reward from the environment, and your objective is to maximize the total reward for reaching B from A, all right? So every time you do a step and you receive a reward, you don't know if that is a good reward or a bad reward, because at the end of the day, your objective is to maximize the total reward for your trajectory from A to B, okay? So in this type of problems, I give you very little, all right? And what you optimize, it's actually defined at the end of the whole process. Now, for those who have seen this type of problems before, you know that a lot of the ideas involve exploration and exploitation. And what I mean with that is, if you are at, let's say, at a given state and you want to move towards B, you have the choices to either move to a state that you have learned to have high reward, or to actually take a step in a territory that you know nothing, because potentially that may have the highest reward. Okay, so you either explore or exploit, and the balance of these two constitutes many of the algorithms that you can learn in reinforcement learning. Certainly I can say that the algorithms in reinforcement learning are way more complicated than the algorithms in supervised and unsupervised learning. But the good news is that many of the algorithms, especially in supervised learning, are a significant ingredient of the algorithms that you need to have in your portfolio when you produce new methods for reinforcement learning. Okay, so let me move directly to this polynomial regression problem. So what you see is I have a generating function, that's my sine 2 pi x. So I take a few training points, x's, and these training points, I compute the values of the sine function, and then I assign some, let's say, Gaussian noise. So that way I produce these circle points. This is my training data. So the idea now is to come up with a fitting with some, let's say, polynomial to this training data. I don't give you what the function that generated the data is, and remember the data have been polluted with noise, so your job is to somehow learn the underlying function or approximate the underlying function using only these 10 training data points. Okay, so how are we going to do this fitting? So we're going to use, let's say, for simplicity, a polynomial that looks, a regression function that looks like this. It involves powers of x up to order, in this particular case, m. The coefficients w0 to wm are the unknowns. So once we can compute those, then we have a fitting to the data. And w0 is called the bias parameter. Actually, I can make w0 to look like similar to the other w's by putting next to it x to the power 0. And we may do that actually in the equations that you will see in the follow-up slides. And so we need to compute the coefficients, we need to minimize some loss function. And the obvious loss function is to minimize the error we do at the training data points. So at the training axis, Tn are my labels. So I want my regression function to approximate Tn as close as possible in this L2 error norm. And so I'm minimizing this square error. And how do you compute W's? You can take your assumed regression function in terms of these powers of x, plug it inside this error function, take derivatives with respect to each of the W coefficients, and form a linear system of equations, and that will be the least square solution that you see in the bottom of this slide. Okay, so basically what you have is A times W equal to T, where A and capital T are defined from your training data set. In principle, the error function is nothing else but minimizing the square distances of these vertical lines that are basically the distances of your target Tn values from the regression function at the given xn input locations. All right, so let's see this in action. If I try to fit a polynomial of order 0, so that's a constant basically, you realize that's a very bad fit. If we put a linear, a straight line, that also looks a very poor fitting to these sign-generated training data points. Now, if somehow we use a third order polynomial, you can see now that the fitting is way better, okay? And if you keep increasing and you go to m equal to 9, somehow now you learn what overfitting is, right? Your training error has become 0 because you can pass your regression function through all the training points. However, you anticipate that this regression function will have very bad ability to generalize and give you the correct target values for new x's that you have not seen before. And you can see that for some locations x, the values of this function is way away from the sine function. So obviously your test error that we will see shortly is going to be enormous. So remember, in this case, we have a polynomial of order 9, and still in all the previous examples, we have 10 training data points. Now, how do you define in a good way this sort of a measure of the error that you can plot? We use what's called the root mean square error, which is basically a normalized version of the error function that I gave you before, computed at the least squares estimate for W. But now you notice I normalize it by n. So effectively, this allows me to compare different size training data sets. And then I take a square root, so that way the units of this error are the same as the units of the target values t. And if we plot the values that you saw in the previous examples for the training data set and for the test data set, they look like that. Both errors go down up to polynomial of m equal to 3. Then from 3 to 8, the error has effectively been stabilized. And then after that, when the complexity increases to 9, the test error blows up and the training error goes down to 0. So certainly for this particular case, you can select m for any values between 3 to 8, and that will be sort of a good fit. But obviously, we want, in the more complex case, to know, without necessarily having to do all of these plots for all of the different models, we need to be sure that somehow we do not overfit. So let me tell you exactly what's going on when you overfit. If you go and compute these coefficients W0 for the case m equal to 9 and using 10 data points, you realize that these values become very high positive numbers, and then immediately after that the next W is a very negative large number. So we have this plus minus very big W's coming in the picture, and that is very typical outcome when you do overfit. Okay, so effectively we notice here that when you increase the complexity of the model for a given data set, you have no choice basically but to overfit. Okay, and so in some sense, if you remember, my training data points have been defined by the sine function plus some noise. So essentially what we're doing, we're actually fitting this regression function to noise, and that's the result of overfitting. Okay, now let's make things interesting, and the way we're going to make them interesting is by increasing the number of training data points to 15. So now I'm going to still use a 9th order polynomial, and you notice suddenly there is no overfitting. All right, so that's interesting. So we increase the number of points, and somehow I can afford a higher complexity model without overfitting. So m equal to 9 is not an issue. And actually, if you use 100 training data points, your regression function looks even better. And so effectively, you know what that says? That the more training data you have, the higher the complexity of the model that you can afford without having to worry about overfitting. Okay? Now, it's sort of a concerning issue, and it's a concerning issue because somehow you have the amount of the training data dictating for you what the complexity of your model should be. And in our case, the complexity of the model needs to be defined directly by the sine function, right? This is what defines the complexity, not how much data I gave you. I mean, we know the complexity is the sine function. We need to discover the sine function, so somehow the data should not have this influential role in controlling the complexity that your model can afford. Okay, so this overfitting issue that we see here for these least squares type of problems is the same as the overfitting problem that appears when we do maximum likelihood, and not surprising, maximum likelihood and least squares will turn out in the models we will see today to be exactly one and the same thing. Now, let me say something about Bayesian models that you're going to have to wait 1 or 2 lectures to learn more about Bayesian regression models. I remind you that in Bayesian regression, the predictive distribution is an integral of the likelihood times the posterior with all the parameters integrated out. So in a Bayesian setting, you can afford literally way more parameters than number of training data. Okay, and the reason is because you do integrate these parameters out, there is no overfitting. Okay, so in this particular case, the order of the polynomial m can be way higher than n. Okay, so effectively what is happening in a Bayesian model, the model defines the effective number of parameters, right, that can identify from the data, and in some way automatically adapts this effective number of parameters to the size of your data set. Okay, if you remember, we talked that when we have overfitting, that the coefficients W take this very large and very small negative, I mean, in magnitude, either positive or negative, very large values of W. Okay, so somehow, if we can control the magnitude of these coefficients W, maybe we can avoid overfitting. And the way this can be done is with regularization. And this is your first look at regularization. So in addition to minimizing this square error that you see here, all right, in your training data set, you now also have an additional objective function that says, you know what, keep the magnitude of these coefficients W from, control their magnitude, don't allow them to be very big, okay? This lambda is not a penalty number, so it's not a huge number. Actually, it can be very, very small, like 10 to the minus 9, okay, or even 10 to the minus 20. It's a regularization parameter, and it turns out this regularization parameter is the key parameter in this model that controls complexity. I mean, of course, we have m, the order of the polynomial, and we have the type of basis functions maybe we use, but lambda here is the key parameter that controls complexity for the model. So if you minimize this new objective function with regularization for our regression function that had this x to the power j type of terms, what you actually get is you get a similar system of equations as with least squares, but notice now that the matrix A has in the diagonal an additional element, lambda, which is our regularization parameter. So effectively, what is happening here, the original matrix A is not well posed, okay? And by adding lambda, that matrix A becomes well posed in a way that you can solve the system of equations A times W equal to capital T. Now, if I use a different type of regularization here, maybe a different norm, the answer will be very different and the effect may be very different. But for this standard Tikhonov regularization, you do get a lambda added in the diagonal of your matrix A. Okay, by the way, let me just say when we do this probabilistic Bayesian setting, we will see that we can produce these regularized least squares estimates like what you see on the slide by using a Gaussian prior model. When we compute the map estimate of the parameters, it will turn out that that map estimate of the parameters will be identical to what you see on this slide. So that, again, is interesting that you can discover these deterministic techniques through a probabilistic setting. But again, we will do this later in 1 or 2 lectures from today. So let's repeat the calculations we did before by introducing regularization. So again, we have these 10 data points. And now I am using a regularization parameter such that log of lambda equal to minus 18. And you notice I use a polynomial of order 9. There's no overfitting, all right? I mean, it's not a perfect fit, but there is certainly not overfitting. Certainly there is no oscillation of the coefficients to very big positive numbers and very negative large numbers. Okay, we don't have anything like that. Now, if you increase the regularization, here the lambda is effectively 1, then a lot of the coefficients W are being forced to go to 0, and effectively the regression function, the only terms that stay are W0 and W1, so you get a straight line more or less. Okay, so here you over-regularize the problem, and the fitting is not very good. Okay, if you actually plot these training and test errors that we saw before versus the regularization parameter, the errors for the training error will increase, because now we're not really fitting only to the training data, right? But we're trying to regularize as well. So the training error increases and we reach some asymptotic values. But notice that the test error decreases and reaches an asymptotic value, and there's no indication, the way I have it here, that there is going to be any blow up and overfitting the way that we saw before without any regularization. Okay. We talked about maximum likelihood. I mentioned, actually haven't done anything yet with maximum likelihood. I told you that it will turn out that the maximum likelihood estimator with a Gaussian likelihood, it will be the same as least squares. And we discussed a little bit about regularization. And we said regularization controls the model complexity, and so it is the main parameter that defines the complexity of that the model can afford. And so we don't have that limiting factor that we had before coming just from the training data set, from the size of the training data set. But I don't want to spend time to tell you how you're going to select the regularization parameter, but in a sort of non-probabilistic way to do that is to actually play with different numbers for lambda and evaluate the performance of the model, maybe using ideas such as cross-validation that I discussed in an earlier lecture. But obviously, this type of methods will be computationally expensive because involve running a regression model multiple times. All right, so what I want to do now is I want to sort of get out of the way the differences in doing regression from a frequentist point of view and from a Bayesian point of view. Okay, so in all cases, right, we have some parameters W, right, that somehow we need to compute to evaluate our regression function. And we will see what the regression function means in a probabilistic sense soon. But effectively, we're going to need in all models to have some sort of a likelihood model that tell us the probability of the data given the regression parameters. And I'm going to define one very soon. So both the Bayesian and the frequentist approaches have a likelihood model that looks like that. Now, in the frequentist approach, W is a fixed parameter. Okay, so for example, you're going to use maximum likelihood estimator or the least squares estimates that I gave you before, and that's your W. Now, you may say, with that said, maybe you have seen in books that this frequentists, they do report error bars on W. And actually, if you report error bars on W, it's like equivalent to reporting error bars on the regression function itself. Where are those error bars come if W is deterministic and it's fixed? Well, the idea is that in the frequentist setting, these error bars come when you change the training data set. So there are error bars over different training data sets D. This is what the frequentist statisticians call the bootstrap data sets. In a Bayesian setting, it's exactly the opposite. W is a set of random variables, and we're going to put a prior on those random variables, and we only have one data set to train the model. Okay, so we're not going to take the data set and split it in bootstrap data sets. We're going to use all of it. If we have data, we use them for training. So W becomes random variables, and that together with the likelihood produce a posterior, and that's where the uncertainties in the regression estimates are coming about. Now, you can appreciate the need for a prior model, and I have shown you, you have seen this picture before, right? If there is a regime where you don't have training data set and you try to fit some regression function, you need to be able to put some prior knowledge here that tells you what's going on, because do not expect that information from this data set will be able to actually do predictions for you in this regime. So you need to have some prior modeling. So everything we learned in the previous lectures are directly applicable, and we will use them line by line in a follow-up lecture for regression models. But we're going to postulate a likelihood, we're going to have a prior on W, we're going to compute a posterior, and if you do that and you have a posterior on W, you will actually be able to also produce a predictive distribution that for any X it tells you what the target value is, and also it tells you what the uncertainties in the target value also are all about. Okay, so everything you learn about the posterior being the likelihood times the prior, we are going to be using these concepts where our parameters are going to be the regression coefficients. Okay, the parameters are going to be the regression coefficients. All right, now for this lecture, I am only going to concentrate on the likelihood model. So I'm going to try to introduce a probabilistic version for regression where I will only concentrate on the likelihood model and tell you about the MLE estimate. But using this slide, you can extrapolate how the calculations will look once we put a prior model and we produce a posterior on W. But today we concentrate on the likelihood, and we try to see why maximum likelihood estimation leads to to overfitting, and we will see also that least squares and MLE they turn out to give you the same estimates for the parameters. So let me remind you what we have seen extremely fast with the univariate Gaussian. You remember when we had a nice Gaussian with unknown parameters mu and sigma square. So somebody gives us data X and then says, go and compute for me mu and sigma square. So we computed the likelihood, and I'm not going to go through the repeating the same things 50 times. You compute the log likelihood, you maximize it with respect to mu and sigma square, and we show that the MLE estimates are nothing else but the sample mean and the sample variance. Okay? And remember, the original problem, we give you data X, right? And mu and sigma square are the unknown parameters. You will see that somehow our regression problem will take the same identical form in a few slides from now. Now, when we discuss about these point estimates, these MLE estimates, we saw that the MLE estimate for the mean is unbiased, and we saw that the MLE estimate for the variance is a biased estimate. So as a matter of fact, we proved, more or less the derivation is given on the bottom of the slide, but we proved that you underestimate the variance, okay, using the sample variance, okay. So sigma squared here is the true variance, sigma MLE squared is the sample variance. And actually, this underestimating the variance was communicated very nicely with this picture from Chris Bishop's book, where I remind you we have a true Gaussian, and we take two samples at a time from that Gaussian, and we try to approximate the mean and the variance of the true Gaussian. And we said when you take the mean and you average the three cases, you get more or less the true mean of the true Gaussian that generated the data. But the variance, using only 2 points, is underestimated. If you take all of these have the same more or less sample variance, so when you average them, you get an underestimation of the true variance of the true Gaussian. And the reason you underestimate has to do with the fact that this sample variance, it is with respect to the sample mean, right? Not with respect to the true mean that you don't know. Okay, so what you see here, this underestimation of the variance, right, is exactly the cause of overfitting that we discuss for least squares estimates, and we will soon see as the MLE estimates for a Gaussian likelihood as well. Okay, so let me introduce a probabilistic setting, very preliminary version. We're not going to get rid of the regression function, all right? So we're still going to have at every x, we're going to try to have a function that somehow approximates the target t, but somehow this function y of x, it will be the mean of some distribution of t for that location x. As a matter of fact, if I can see a schematic, if you take a particular location x, your estimation for the target of that location will be, let's say, this particular Gaussian, the way that I see here. And the mean of that Gaussian is going to be actually corresponding to the value of my regression function at this location x0. Okay, so somehow the regression function is going to be, is going to be the mean of this conditional distribution of p of t given x. Now, usually when you come up with point estimates in statistics, right? Always that implies some loss function, and I remind you the appropriate loss function to get literally the posterior mean, which that you see here as your regression function, is to actually use a quadratic loss function. Okay, so and what I mean is quadratic loss function. You try basically to minimize the error of y minus t square, okay, y minus t square. Then it turns out that the optimal y is actually the posterior mean at that location x. We will see a little bit about these calculations later on, but for right now, I want you to envision that for each location, we're going to have a distribution of t, and the mean value of that distribution is actually our regression function. So obviously, this distribution is going to be parameterized. It will have some mean, and that mean will be my regression function that is parameterized with w. So that's where exactly w is going to come. So before I show you the likelihood model, let me go fast through some example of representations of the regression function. So here is, if we have x to be in d dimensions, using each of the d components of x, you can write a regression function in d dimensions like that, okay? We call all of these problems linear regression models, not because we are having linearity in x, but because the problems are linear in the w's, okay? So even if I had here x1 square, this I will still call it a linear regression problem because it's linear in w. All right. Now here is another regression function where instead of my input vector x, I use some futures of the input vector x, and the futures here are phi of 1 of x, phi m minus 1 of x. So this, you can think of them as either some mappings of x to a new space, the future space, or somehow these are some operations on x that extract literally what the word future means. So you can even think that, if you have x being an image, maybe you rotate, you scale the image, and that's what this type of functions phi1 do. But apart from that, in principle, they can be arbitrary functions that are applied to x, okay? And we will see our analysis can apply it equally well when our regression function takes this form, and I write it here as a vector form, W transpose phi of x, where this phi, this bold phi, consists of all of my basis functions, phi 0, phi 1, applied to x, where for simplicity I have called phi 0 of x to be 1, so this can go nicely with my bias term and make the bias term to look like the other terms in the regression function. Okay, examples of futures. There can be polynomial basis functions, as you see here, can be Gaussians or square exponentials, the way that you see on the right. So this, you notice here parameters mu and variance as squared that you can control, or maybe you can optimize if you wish so. Your basis functions can be sigmoids. Sigmoids are extremely popular because they're, if you model something that you want it to become a probability take values between 0 and 1, you always operate on it with a sigmoid function that squeezes this between 0 and 1. This is the sigmoid function, and the way that I wrote it here, it has parameters mu and parameter s that you can again either a priori define or you can optimize. These sigmoid basis functions are in principle equivalent with hyperbolic tangent basis functions, and you can see the one-to-one relation between the sigmoid functions and the hyperbolic tangent functions. As a matter of fact, you can actually show that if you have a regression, a regression function in terms of sigmoids, you can actually write it in an equivalent form in terms of hyperbolic tangents, where the relation between these w's and the u's that you use for hyperbolic tangents are given, but what you see on the bottom of this slide. So sigmoids and hyperbolic tangents, for all practical purposes, basically are one and the same for the type of things that we're interested in this lecture. Okay, one of the things that I will insist to pay attention is that it makes sense, these basis functions, to have local support. And what I mean with that, remember, wi multiplies the basis function phi I of x. So you don't want really, when wi changes a little bit, to affect the solution everywhere. You only want it to be affected in the support region of phi I of x. Okay, so we would like these basis functions to have local support. There are lots of choices that you can use, right? And I'm not, this is not the right course to discuss about this, but if you want to use wavelets, you can make them to be locally both spatially and in the frequency domain. But Gaussians are very nice local support functions you can use, right? So all of them will work nicely. All right, here is our probabilistic model that this is what we will use in all the remaining lectures. So let's look at the second equation that you see here. We're looking at a given location x. So the target is this regression function plus some noise epsilon. So if you think about the observations that we're getting, right, we computed them using the true generating function, which now we don't have. We have an approximation of it, which is the regression function y of x and w plus some Gaussian noise that has a precision beta. And I remind you, our regression function is phi transpose w, right, where I put all the basis factors, all the basis functions and all the w coefficients, I put them in a vector form. Okay, so what I can write is, I can write that my likelihood model now, so if you give me at a given location x, you give me the target value t, my likelihood model is basically the Gaussian that you see in this picture, okay? When we worked before for MLE estimate for the mean and the variance for a Gaussian, right? We had the Gaussian, and I gave you samples from that Gaussian, and the unknowns were the mean and the variance. Well, here the unknowns are the mean and the variance. The only difference, the mean, comes in this form where really the only unknowns are w. So in essence, whatever we said about the MLE estimates for a Gaussian, they're exactly what we need to apply here to compute an MLE estimate for W and for the noise beta. Okay, the noise beta is taken throughout to be the same. Okay, so a single noise parameter defines this particular model. Okay. So we need to evaluate W and we need to evaluate beta by maximizing this likelihood. And the way we're going to do this, we're going to take the log likelihood. All right, so when you take the log likelihood immediately, so we need to maximize this. And you notice the only place that W comes is on the first term. And so maximizing this with respect to W is the same as minimizing the square error. So immediately we conclude that least squares and maximum likelihood give one and the same answer. And then there is beta coming on the first term and on this term, and this will give us an estimator for beta. What those are, okay, here is the estimation so this is the MLE for the variance, 1 over beta, beta is the precision, and this is my sample variance. And again, we don't know the true mean, so the true mean here is approximated with the sample mean, which is my regression function for using the MLE parameters W. Now, if actually you want to produce a probabilistic model for predictions immediately, right? What you can do is you can use an MLE plugin approximation and your likelihood model, and you can say, if you want to do predictions at any location X of your target value, it's basically your likelihood model where your parameters that you use are your MLE estimates, all right? I'm not suggesting that this would be a reasonable thing to do, but there is a probabilistic model that gives you a mean and error bars that at each location X, you know what the target is, and also you know what the error bars are, the way we have discussed in earlier lectures for the Gaussian. Now, a few more examples of this, likelihood, maximum likelihood estimation. So on the left, you see a fitting of this linear polynomial in 2 dimensions, x1 and x2. And then on the right, you see fitting a quadratic regression function. So, and in both plots, you see how the regression function will look like. Okay, so let's do this more formally and try to produce a metrics form for this MLE estimate for W that will remind us least squares solutions from linear algebra. So the problem again is we're given these X vectors, okay? This is my training data set, and I denote this with bold because X1, X2, etc. can be vectors. And I have these targets, and I assume the targets are real numbers, okay? So this is my likelihood model, all right? We take the log likelihood, it looks like this, nothing different from what we did before. Or if you prefer, you can actually minimize the negative log likelihood, right? That looks like that. All the same things for me, okay? We said that when you expand basically this error term here is nothing else but what actually we minimize when we worked on the least squares problem, okay? And don't be bothered that in the least squares problem we didn't use basis functions because, it will be the same thing, and we will see the derivation today. But minimizing this will give us a least squares estimate for W, and maximizing this minus term here will actually give us the same estimate for W. Okay, so this is what is called the residual sum of squares, right? When you divide this by n, you get this mean square error, okay? And again, this error here is minimizing the square of these distances of my training labels t from my regression function, okay? And And what you actually see also here on the right is some contours of the of the likelihood that indicate basically that there is a unique minimum for the parameters W when you maximize the likelihood. Okay. So let me do the algebra now, right? Because I want to produce an equation for W in a nice matrix form. So what we're going to do is, this is the way it is written here, right? This is scalar, but W is a vector and phi is a vector. So when we take derivatives with respect to W, we're going to get basically a vector here. And I am writing this gradient of the log likelihood as a row vector. So when you take derivatives with respect to W, you're going to get a phi transpose here. All right, so you're going to have Tn times phi transpose and then minus W transpose, and then you have phi transpose. And phi transpose, right, is the outer product between vectors. So this is a matrix, all right, and this is a vector. Now, I'm going to show you the algebra in the next slide, but effectively, the system of linear equations that you get is this design matrix phi transpose phi times W equal phi transpose T, where this capital phi, you will see soon, is basically the vectors, these basis functions evaluated at all the training data points x1 to xn. Okay, so this will be my design matrix, and I call it capital phi because effectively my design matrix is not defined in the original space X, is defined in the future space phi of X. So I denote this with capital phi. So what is capital phi? Okay, and I will come back to the equations on the top. So this is capital phi. If you look, every row in the matrix phi is corresponds to one of the training points x1, x2, all the way down to xn. Okay, so again, so the first row is basically the transpose of the vector phi transpose of x1, where phi transpose of x1 is involves all the basis functions evaluated at x1. So the first row corresponds to the training data point x1. Okay, similarly for the second row, similarly for the nth row. So always remember, every row is one training data point, and then in every column you have each of your basis functions. So if you look at column 1, you have your basis function phi0 evaluated at all of your training data points. On the second column, you have phi1 evaluated at all the training points, etc. Pay attention to the notation. When you see phi of x, right? That is the column vector that evaluates all the basis functions at the point x, okay? But when you see this calligraphic phi, that is the column vector that involves the ith basis function evaluated at all the training data points. So for example, this is the first column is the calligraphic phi0, right? Phi0 means I take the basis function phi0 and I evaluate it at all the training data points. So there is a difference again of all the basis functions evaluated at the same training point, or all the training data points operated by the same basis function. And that's what I get in my columns. So if you take the equation that is derived by maximizing the log likelihood, you can actually convince yourselves that this phi transpose with summation on n is nothing else but this capital phi transpose times phi, all right? And you can similarly see that Tn phi of xn is nothing else but phi transpose t. And that's what I have here. And hopefully that reminds you of a least square solution. And the W that you get there by inverting phi transpose phi is what is called the Moore-Penrose pseudo-inverse. Okay, the estimate for the variance we already have seen in an earlier slide, so I am not going to repeat. But let me just say that there is a unique MLE estimate for these Gaussian models, and this has to do with the fact that the if you look at the negative log likelihood, it has a unique point, a unique minimizer, because it's a convex function. So what you need to know here is that you need to know what does convexity means. And I define here with these images convexity both in the context of region. So this is a convex region, this is a non-convex region. And I remind you, a convex region is a region where if you take any points x and y and you connect them with a straight line, every point on that line belongs to the region. Okay? Now, in the context of a function, these functions here, like theta log of theta, is a convex function because if you take this point x and y and you connect the values of the function at those points and you take a weighted averages of the values of this function at the endpoints, for example, if you take this value is always greater or equal to this value here of the function. Okay, that's what we call a convex function. This is a concave function, so log of theta is a concave function, but later on actually we will use minus log, because minus log will be a convex function, so we will be able to utilize that fact. On the right you see a function that is not a convex, is not a concave, right? And you notice that it has multiple local minima. That's not what we get with these maximum likelihood estimators. So these maximum likelihood estimators have a unique, right? Have a unique minimum because of the convexity of the negative log likelihood. All right. If you want to produce iteratively an estimate, an MLE estimate for the parameters W, so if you want basically to update the estimate for W1 training point at a time, you can use the Robbins-Monroe algorithm. And the whole idea here is you can do this because if you look at the error function that has to be minimized to compute the MLE estimate for W, you notice that this error function is summation over each training data point. Okay, it's a summation over each training data point. So here's how the so En in this particular case would be 1/2 of this parenthesis square for the training point N. Okay, so without remind you everything about Robbins-Monroe, effectively, iteratively, if you have an estimate of the parameters W up to up to now, you can use your previous estimate, move in the direction of the negative gradient, evaluate it at your nth training point, where eta is some training rate, and then update the parameter. And if you look very carefully in the way this update looks with a gradient for our particular function, you notice that you have an error signal. It basically tells you how far is your current prediction at xn with your previous W's from the training point labeled Tn, all right, how far, that's the error that you commit with your already the previous guess of your regression function. And then you see it's times the future for the function for the data point xn. When we discuss later on about the generalized linear models and the exponential family, the algorithm that you see here for updating W, you will see that it is very general, and you can apply it to many type of different distributions for many different problems. Okay, so this is the error that you commit on the nth training data point, and this is the future evaluated at the input xn. Okay, and this algorithm actually is so popular that comes with its own name, and it's called the least mean squares, or if you want to search on the web, this is what's called the LMS algorithm. Okay, let me discuss a little bit about robustness. Okay, if you remember, we use a Gaussian likelihood model. So the error that we minimize is basically quadratic, okay? Is basically the target value Tn at my training point n minus the value of my regression function square. So if somewhere you have an outlier, a point that is far away from reality, you're penalizing your model quadratically for the error that that outlier brings. And that is not good. So you would like to somehow have more soft penalization of outliers. And the way to do this is, instead of having an L2 norm, maybe you can have an L1 norm, all right? The way it happens is you're going to have to move away from your Gaussian likelihood. And for example, you may want to use a student T or a Laplace likelihood model. And I'm writing here the Laplace prior. You notice instead of a quadratic, you actually have just the absolute value. Okay, so all of these distributions are distributions with heavy tails, all right? And the result of these distributions, the way we discussed earlier, is robustness. And this is a beautiful schematic that demonstrates robustness in regression. So if you have three outlier points that you see here on the bottom, you can see immediately the least square solution with the Gaussian likelihood, okay, effectively has moved towards the outliers, but both for the case of the Laplace and the student T likelihoods, the effect of the outliers has literally been minimal. Okay. Now there is another way to do this type of problems, because using so if you think about using the Laplace prior and trying to do maximum likelihood estimation, the trouble you're going to have is that this absolute value function is not differentiable, right? So the absolute value function is not differentiable. So you will not be able to use, let's say, a gradient method to do the optimization problem. So the way to fix this is, because the Gaussian likelihood seems to perform well if you don't have outliers, how about if you use a loss function that is quadratic in some neighborhood, of the distance r to be less than or equal to some distance delta. So if the error that you commit with your regression function to the target values is within a delta ball, all right, you are using a quadratic loss function. But if it is away by delta, then maybe you use something that is penalizes only proportionally to the to the absolute value. Now this model, then you may say, how do I match those things at when r is equal to delta? Well, you can actually match both the values and the slope of the function at r equal to delta. And when you do that, you effectively get, you get an approximation, you get a loss function that is differentiable. And it has the benefits of the Gaussian like loss function that is quadratic, but also has the benefits of this absolute value loss function when the error is higher than delta. So this loss function that you see here is called the Huber loss function, and is very popular. It's very popular because it takes the benefits of both the simplicity of the Gaussian likelihood and the Laplace prior, but in a way that allows you to use gradient methods. So the loss function that you get is differentiable. So you will see this being used often in the literature. Okay, now there is a last approach that you can use to address this problem without having to solve this optimization problems with gradient methods. You can use instead linear programming methods. And I'm going to explain in a second what exactly the new objective function is going to be. But let me just say the problem is being transformed from a problem in m variables, these are the coefficients w, to a problem with 2n plus m variables, and the 2n plus m variables are these new variables Ri plus and Ri minus for each of the n training data points. And what is Ri plus and Ri minus? They effectively define if you are above the regression function or below the regression function, and the magnitude of Ri, of the distance from the regression function, is really Ri plus and Ri minus, and the objective is to minimize this objective function, that is summation over all the training data points of Ri plus and Ri minus, but now with respect to W, with respect to Ri plus and Ri minus, in such a way that W transpose Xi plus Ri plus minus Ri minus is equal to Ti. Okay, so you can think, the regression, if you evaluate at Xi, your regression function W transpose Xi, this is away from the target Ti, but if you move, let's say, above by some distance, right, then it becomes equal to Ti. So this, think of this as what is called slack variables, and when you optimize this new objective with this constraint, and also with the constraints that Ri plus and Ri minus are greater or equal to 0, you can solve this in a higher dimension space, 2n plus m, using what's called a linear programming algorithm, which is a very efficient way to actually address this particular problem. All right, let me finish here. The next lecture is going to go back to regularization, introduce different sorts of regularization, and we will take the general MLE estimate that we got with the design metrics phi and figure out how that problem can be regularized, all right? And then slowly in the 2 lectures from today, we're going to start talking about the Bayesian setting for this problem and see how we can reproduce with a map estimate the regularized solution that we will see in the next lecture. And of course, beyond that, how to produce the whole posterior of W and how to come up with a predictive distribution. You will be surprised that actually the results will be trivial, because most of the calculations are calculations we have done with Gaussian models earlier in the course. All right, I will stop there, and I will see you in the next lecture in 2 days. Bye.